Hello all. So as you know, recently we've been talking about optimization problems. And the way we've been doing that is giving you a function, then you take the derivative, set it equal to 0, and you find the critical points, and you decide if it's a maximum or a minimum. And that's all fine and dandy, but that's not how the real world works. Typically, there's a problem in the world, and you have to fix it, so you create your own equations, and then you figure out how to solve the problem. So that's what we're going to practice today. As you can see on the slides, we have found maxes and mins of functions. Today we'll create our own functions, and this is related to in many careers like engineering, biology, chemistry, marketing, architecture, all of those things. You need these skills to work in those fields. So we're going to go through an example, and I have put a lot of detail into the slide so that you can come back and look at the process, because this process is pretty standard for what we're going to be doing in our future homeworks and ideas that we're going to be fleshing out. So as you can see here, it says a manufacturer needs to cut pieces of cardboard with which to make open boxes, so without the wings, right? Just open. She wants each box to have a square base. That means the sides are the same, right? We know what a square is. And to have a volume of 4 square feet. What is the minimum amount of cardboard that needs to be used for each box? So this is clearly a minimization problem. This is something that we look at the world and we go, okay, how do we fix this? How do we solve this? So first things first, draw a picture. Every single time you need to draw a picture. Okay, so basically she's cutting squares that look like the left picture, and we're making a box that looks like the right picture but without the wings. So you should label the sides. In the picture it's labeled length, width, and height, but really, as you'll see on the next slide, the bottom is a square, so we can label it X and X. So for us in this problem, we have two quantities that we're working with. We're working with area because we're looking at the area of the box, and we're dealing with volume because they gave us what the volume has to be. So we'll write down the equations that we might need, which will probably be the volume and area equations, with any known information specified. So we'll have to define a variable first, though. So like I said before, it's a square box. So we'll say that x is the length of one of the sides of the base, which means it's also the size of the other side, and h is the height. So on your picture that you're drawing as you're watching these notes, you need to draw a box with each side labeled. So because of the labels we picked, we can say that the area of the box without a top, right, so it has 5 sides of cardboard, is the area of each side, which is x squared, which is the bottom piece, and then the xh, 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 xh are all the 4 sides, and the top is missing, so we don't have a second x squared. So the area is x squared plus 4xh. Okay, great. And the volume of the box, because the volume of any box, is length times width times height. So in this case, the area of the base is x squared, which we already knew from up top, and we multiply that by the height. So x squared times h is the volume, which has to equal 4 because that was given in the problem. Remember, it said that the volume had to be 4 square feet. So it's important in these problems that we don't get lost along the way. We have to know why we're doing what we're doing and what we're doing. So we're going to refocus. We're trying to optimize, which we know will require a derivative. A big hint is that we've done that, for the past several weeks. But we'll need a derivative to maximize. And taking a derivative for us means we need a function of one variable that describes the thing we're optimizing, and I say for us because we don't do partial derivatives, which is something you'll get to in a future math class. But for us, it needs to have one variable and a function that describes the variable we're optimizing. So we're optimizing area, right, because we're finding the minimum area needed. So we want to express area as a function of x. We will use the volume equation to solve for h. So since x squared times h equals 4, you divide both sides by x squared and h equals 4 over x squared. And thus the area of the box, which I'm calling a of x because that's a logical variable name, equals x squared plus 4x times h, but in this case h is 4 over x squared because we solved for that. And when you simplify, that equals x squared plus 16x. So now we have a function of one variable that describes the thing that we're minimizing, which means we can take the derivative. So when we take the derivative, which is just basic power rule stuff that we've been doing for the entire section, we get a prime of x equals 2x minus 16 over x squared. So now we're back to the stuff that we've been doing this whole time. We set the derivative equal to 0 to solve for critical points. And when we say 2x minus 16 over x squared equals 0, this means that 2x equals 16 over x squared. You multiply both sides by x squared and divide both sides by 2, so x cubed equals 8, which means x is 2. Okay, so this is our critical point. And we check, just like we have been in all of the previous lessons, if this is a min or a max of our area function. So when x is 3, so to the right of 2, the derivative is positive, so the area function is increasing. And when x is 1, left of 2, the function is decreasing. Since the function is decreasing then increasing, there must be a minimum at x equals 2. So we need to interpret this, because if we are in a job somewhere and we're expected to solve a problem, we can't just say an answer is x. Okay, we have to interpret our results so that we can communicate that to others. So yes, this means we use words, we use punctuation, we use capital letters, all the stuff you've learned in English, we use it here. So a possible sentence, because there are many, to describe the solution for this would be, when we cut out squares of cardboard, making each side of the square be 2 feet long will minimize the cardboard needed to create an open box that holds 4 square feet. So this is the end of the example, but the process is similar throughout all of these problems. So there is a discussion that you will go to. There's a discussion board that will be posted shortly online. On this discussion board, you will be required to come up with a problem. So I would recommend coming up with a problem that you might enjoy, might be interesting to you, and you'll be required to come up with your own equations, because that is what you have to do in the real world. So your homework is the summative assignment that is posted online. Don't forget to do it and start early. And that is all I have for you today. Have a wonderful day.